All right, I think we have enough tools now in our toolkit to be able to discuss this notion of a Riemann sum. So, suppose we're given, so let's let f of x be defined on a closed interval AB. Let's let delta be a partition. All right. Now, here's the next piece. Let C sub I be a value C sub I is a value in subinterval I subscript little I. Now, what the heck does that mean? All right. Here's A. Here's B. Partition x0, x1, x2, x3. So it's a very simple circumstance. There may be many more than this. I'm just keeping it small so we understand the idea. Again, the basic here is understand the idea. This is not a computation you need to be able to do, but these are ideas that we're going to be using to develop the work we're actually going to be approaching. So this is a function. So I have a function defined. I have this a partition, and here's my function. So f of x. Let's throw my function in green here. So we have some function defined up above the axis. All right? We choose a value in each of the subintervals. Subinterval number 1, you're free to choose C to be any number, any value in this subinterval. So in this particular case, C1, this is the symbol for is an element of or is contained in. C1, how about I say, is in interval number 1. Remember, the interval number is the right endpoint subscript. So C1 is any point. It may be in between. It may be one of the left. So C1, I'm just going to pick at random. Here's C number 1. There's C1. C number 2 is in x1, x2. C number 2 is in interval number 2. It may be one of the endpoints. It may be in between. Any value in that interval is permitted. In this case, let's just choose at random. I'm going to choose, suppose in this case I chose C2 to equal the endpoint, not for any particular reason other than just to show you're permitted to do that if you like. And then we choose C3 is in interval number 3. And so I'm going to C3 right there. There's C3. Right? So each subinterval has selected from it what's called a representative value. It's a value from that interval. All right? This is similar. It's not the same thing. It's similar to the notion when we did the first derivative analysis and we choose representatives from the intervals. It's not the same thing, but it sort of leans in that direction of that notion. So Riemann sum says this. We have f is defined. We have a partition. We've chosen a value from each of those partitions. Then the Riemann sum, S, the Riemann sum, is given by the following. It is the sum. Remember, capital sigma means the sum, which means you add all these up. The sum then goes from 1, in this case, sorry, I should do this better. As I goes from 1 to n of f of c sub I times delta x sub I. Now, if that's not enough symbols for you, you need to get out more. Don't get out more because of the distance thing. But yeah, okay. So yeah, this is the sum. Is the sum summation means you're adding together. You take the function value at c sub I, and then you multiply that by delta x sub I. So what the heck does that mean? Well, it means this. In this particular circumstance, what it means is this. When I equals 1, you take C number 1, you take F of C number 1, multiply it by the width. Delta x sub 1 is that width. Delta x sub I is the width of that little subinterval. Whatever that works out to be, that's what you choose. So this is times delta x number 1, whatever that width happens to be. Sigma means add. So notice, order of operations, multiply before you add. So multiply those, plus, now when I is equal to 2, that's C number 2, F of C number 2, multiply by width of interval number 2. Width of interval number 2 is right here. There's C number 2, there's width of interval number 2, plus, and I'll finish this up down here, plus, and when I is equal to, in this particular case, n was equal to 3. So as many as we need, you do this for all the subintervals. In this particular case, n is 3. So the sum goes from I equals 1 to 3. In this particular case, n is 3. So I take C number 3, F of C number 3, and multiply it by the width of this is subinterval number 2, delta x2. This is delta x3. Multiply that by delta x3. Compute, multiply, compute, multiply, compute, multiply. Add them all up. That is a Riemann sum. Why that's important at this stage of the game from your side of the video camera is not obvious at all. This idea, this notion of a Riemann sum, this is one of the most important ideas going forward from this point on into the calculus. This is used in physics, this is used in chemistry, this is used in biology, this is used anywhere that integral calculus is used from here on out. This is one of the key ideas. This is fundamental to the work we're going to be doing. Simple ideas. An interval chopped up, pick a number from each of those, define the function, multiply by the width, add them all up, and you get a number. Is it clear? When you do this computation, this is going to be a number multiplied by a number. This is going to be a number. This is going to be a number. This is going to be a number. And then when you add those three numbers, you get a number. This is a number, a numeric value. This is not a function. It is a specific numeric value. That's the notion of a Riemann sum. You don't need to be able to reproduce this. But when you see this collection of symbols, you should recognize that is a Riemann sum. Why that's important, we'll take forward in the next lesson or two. But that's the basic idea. This is a Riemann sum. All right? Summation of f of c sub I. C sub I is the value taken from each subinterval. Delta x sub I is the width of each subinterval. Multiply those, add those all up. That's the value of a Riemann sum.